The following is the visualization of the gradient, divergence, and curl, colored by yellow, orange, and magenta. And what we see here is we have a scalar field and a vector field. So the question is, how do we get such gradient, divergence, and curl? And later we will be using it for doing some electromagnetism. So this is Understanding Physics, and make sure to like and subscribe, and also please check the notes in the description for the notes throughout this entire discussion. So let's go first with the definition of a scalar as well as a vector. So last time when we talked about in classical mechanics, we talked about the invariance of such object. But in here we'll be discussing something that is pretty simple. A scalar only has a magnitude or just a number, which doesn't change if you change your coordinate system, while a vector has magnitude as well as direction. And so therefore, if you rotate your reference frame, you would have a different vector, even though they are the same vector, but they are expressed in two different ways. So these two are objects that describe physical quantities, and normally we use something which we call as the field. So we have a scalar field and a vector field, corresponding to the collection of the scalar or the vector throughout the entire space and time. So let's ask about how do we manipulate such vectors around, which we will call as vector algebra. So the very simple thing to know about vectors is that it it has components as well as the magnitude. So if you have a vector in two dimension, you could always express it between two different independent vectors. Normally they are orthogonal to each other, so you could call this vector v, which has component vx and vy. So if you extend this for three dimensions, you could get the length of your vector just to be Pythagoras, which is vx squared plus vy squared plus vz squared. Now you could also use some geometry to figure out what is the vx and the vy. So let's say if this angle is alpha between the x-axis and your vector, it, it means that you could figure out the component in the x direction just to be the length of v, multiply this by the cosine of alpha, which is coming from geometry. Adding vectors up is also pretty simple. So you might have already known how to sum up vectors. You just put one end into the other, and summing them up would just be putting them all together, a plus b. And you could just do this by also doing geometry. So if you take the x-axis and the y-axis, it's pretty much just the c component, or this is a plus b, in the ith component would just be ai plus bi. It's quite simple to do such summation. And doing multiplication by a scalar is also pretty simple. Since if we assume that if this is a plus a, this would be the same thing as doing ci equals to a plus a in the I direction. Or this will be just 2ai. Or we could just denote this as 2 times a in the ith direction. So doing multiplication by a scalar literally means that you multiply it for each of the terms. So there are some properties for such addition. First of all is that it is associative, which means that you could actually flip around the parentheses. So a plus b, a plus the vector b plus c is the same thing as the vector a plus b plus c. It's the same thing. And also, it is also commutative. Commutative. Which means that a plus b is the same thing as b plus a. So what we know is that if you add up two different vectors, you would always get a vector. If you multiply a scalar by a vector, or technically a vector by a scalar, it would result into another vector. So to do multiplications between vectors, So if you want a vector multiplied by another vector, there are two different ways for you to do it. First of all, you have the dot product or the inner product. The dot product is pretty simple. A dot B is the same thing as the sum of I of AI BI, which basically means you just multiply each of the terms one by one and then sum them all together. And there are properties for such dot product in which this is the same thing as taking the length of A times the length of B, multiply this by the cosine theta. So this pretty much tells you that you just go into the component in the same direction as B. So you drop your A into the B coordinate system, and then you would multiply both of the lengths together. Now this will give you certain properties, such that if you have A is tangential to B, A dot B will always be 0. And also you could also express the length A just as the square root of the square root of A dot A. After the dot product, we could talk about the vector product or the cross product. Cross product. So the cross product has a very different way to compute it, in which C equals to A cross B. This can be represented as the matrix determinant of the directions I hat, J hat, and K hat of AX, AY, AZ, BX, BY, BZ for the IJK corresponding to the directions here, X, Y, Z. Something to note about this is that if you already know about linear algebra, you would know that flipping the rows would result into the negative determinant. So B cross A is negative A cross B. It is anti-commutative. And so from this property, if you substitute A cross the B into A, this would mean that you would figure out that A cross A has to be 0, otherwise there is no other values for it to resolve into. So we can express this A cross B into the notation for the length of C. It would be the length of A times the length of B, multiply that by the sine of theta, the length of sine theta. So we have talked about the scalar product and the cross product. And so now we could actually do a much more interesting case where we would have a triple scalar product, which means that you would do a scalar product but with 3 different vectors. And so you cannot do A dot B dot C because A dot B would mean that it is a scalar, dot C it results to a vector. But we want it to be a scalar in the end. So this would mean that one of them has to be a cross product. So we'll do A dot B cross C, in which B cross C is a vector, so we need to have the kh in there. So this would later just become the determinant of each of the components, like so, bx, by, bz, cx, cy, cz. And this would mean that this is the same thing as negative b, a cross c. You could also do some other permutations, and it will result in the same cyclic pattern. So after we have talked about the scalar product, we can talk about the triple vector product. The triple vector product. So you can expand the triple vector product, which is A cross B cross C, here. And you could prove that this is just B of A dot C minus C A dot B. So what this tells you is that it has a component in the B direction and the C direction. So finally, if you want to do something that is a bit more interesting, is to do division by a vector. And this is something that is not really frequently observed, but I will show it in here. So if you have a scalar, which is a dot x, in which x is a vector that we want to know, we want to ask what is x such that this would equal to c. This is the same definition for division in scalars, but now we are doing this with scalar product and cross product. So a way for you to do this is to actually make x to be, first there is a direction in the a vector, as well as there is a normal vector that will dot it to the a vector, would result into 0. So if you plug this in, this would be k out of the length of a squared equals to c. This means that you could figure out what k is, which is c over the length of a squared. Therefore, x vector must be c over the length of a squared a vector plus the n vector, where n could be any vector that is perpendicular to a. So we can also do the same thing for the cross product. If you have a known vector, and this is a vector cross the x vector, we want to ask what is the x here. We can use the same assumption, and we know that if a vector cross the a vector has to be 0. Therefore, c vector must be k of a cross n. Sorry, there's no k anymore. It's a cross n vector. Now from this equation here, we can get two different information. First of all, a vector is perpendicular to c vector. Second of all, n vector is also perpendicular to c vector. And so with this, we could figure out that the n vector has to be something that is perpendicular to c vector as well as a vector. So we could just rewrite it as this, multiply this by a constant, a scalar constant. So instead of writing it like this, we'll just do a cross c, since it is much more algebraic. So now if you plug your n vector here into the equation again, what you would get, this is a cross a cross c vector, multiply this by p, must be the c vector. And so you could use the property that I have already given, in which a dot c vector, multiply this in the a direction, subtract this by a dot a vector in the c hat direction, the c vector, and this must be c vector. Now you know that a dot c is perpendicular, which means that this front side would be 0. Therefore, what you would get here is negative p of the length of a squared c vector must be the same thing as c vector, or basically p is negative 1 over the length of a squared. So now we can rewrite everything into a single equation. So let's say if it needs to fulfill the condition for the scalar c and for the vector c, what we'd get for x must be the c cross a plus ca divided by the length of a. This is what we will get. So we have talked about the general rule of vector products. So now we want to do a gradient. And so a gradient is pretty much just a directional derivative, or the expression of the directional derivative. So if you choose a direction, let's say in the ds vector, this could be expressed as dx in the I hat, dy in the j hat, and dz in the k hat. And so if you're interested in a scalar value and you want to do the derivative within this direction, this could be expressed as a partial derivative. So we could do it for the x direction first, dx over ds, and then we can do it in the y direction, dy over ds, and finally in the z direction, dz over ds. So the property of a directional derivative is that it will pretty much tell you about the slope within that direction. And so if the directional derivative is 0, it would mean that you would get a scalar value of xyz, and it has to be constant along the s vector. And this is what we call as an equipotential or a level surface. Equipotential. So now we can try to define what gradient is. So gradient can be written, so if you multiply everything by ds, you could get d phi equals to partial phi over partial x dx plus partial phi over partial y dy plus partial phi over partial z dz. And so you could just rewrite this as something, which we'll denote this as nabla phi, dot ds, in which ds is your vectors, right? So what's nabla phi? This is what we call as the gradient, and it has value of partial phi over partial x in the I hat direction, partial phi over partial y in the j hat direction, partial phi over partial z in the k hat direction. So now what you observe here is that this is a vector quantity, and then if you dot it with the ds vector, you would get the d phi. Now, what physical meaning does it have? If you re-express this into the length of nabla phi with the length of ds cosine theta, you could observe the following. If the gradient of phi and the direction s is the same, which means theta is 0, it would mean that you would have the d phi over ds to be the largest, or it has the largest slope. And that is exactly what is the definition of a gradient. This thing points in the highest slope. That's the first thing. So we can now go back to our simulation in which we see this yellow vector is always tangential to the equipotentials, which is shown in gray, and you could always see that it is always pointing towards the higher slope, in which it is not really written here, but you could visualize it in a much more deeper detail. So this is the expression of the gradient in the rectangular coordinate system. But what about if we think about the gradient in the spherical polar coordinates? So you could re-express your d phi into each of the coordinates. So we'll use a different phi. We'll use this phi, okay? So it's d phi over dr, which is the distance from the origin. And then you also need to consider the component in the theta, where theta is the angle from the z-axis, something like that, the theta. And then you could find the angle phi, which corresponds to the angle between the x-axis and your vector after you project it towards the xy plane. So that's your partial phi. Now you could figure out what's the ds vector here. The ds vector in here would be, so if you only change the parameter r, it would be a change in the a hat direction. So it's the a hat r would be the dr. After that, if you think about the role of the d theta, this would be a very small change like this here, in which this is your d theta, and with the length of r, which means that this change here would be r times d theta. So it would be r d theta in the a hat theta direction. So what about the change in the parameter d phi? So if you observe this change in angle, there should be a change within this direction here, where your z-axis points out of the screen. So this would be the length of r sine theta, which is this length, and this is d phi, which means that the total change would be r sine theta in the d phi, right? And the direction, we'll call that as the phi direction. So it's r sine theta d phi of a hat phi. So now you could figure out what is the gradient phi in terms of the spherical polar coordinates, which is ar direction of d phi over dr plus a hat theta in the 1 over r partial phi over partial theta. And lastly, in the a phi hat, it will be 1 over r sine theta partial phi over partial phi. And this is the gradient for the spherical coordinates. So before going to the idea of the curl and the divergence, we should know first about vector integration. So we can always take the idea from single variable calculus and just use the definitions. Let's say the integral of f vector dl vector, where dl pretty much tells you about the path that you are integrating each of these vectors, where dl vector pretty much tells you about the small length here, dl vector. So if you do the dot products, you could just do the same thing as the sum when your when your n goes to infinity. The limit as n goes to infinity of the sum from I equals to 1 until n of each of the vectors fi dot the small lengths li. And so you could also denote a contour integral in which it tells you about a loop that its start and the finish is the same, but this is not generally 0. Instead, they normally have a value, but when it doesn't matter about what path that it take, you could just write it as this guy instead of having a index for the path. You could do the same thing for surface integrals. So f dot n hat in the dA. So this would basically mean if you have like a surface here, let's say it's something like this, and then if you denote the n hat direction, so you could sum up all of the f vectors. And something to note is that the n hat should be always the same. So the convention is normally pointing outwards. So throughout the entire surface, you need to make sure that this n vector always points outwards. So anyways, this is just convention. So if it has a different convention, it would have a negative value. But you could also do the contour integral, same things. So if you have, let's say, a sphere, something like so, you could just do the surface integral and denote it with the circle here. And same thing as before, if it is dependent of the surface, you would need to write an index, otherwise you don't need to. Finally, if you want to do a volume integral for vectors or for scalars, you could just do pretty much the same definition for Riemann sum. So you just sum up each of the values for each of the small volumes. So this would be a scalar, and this would be a vector, in which you could just do it term by term. So we are ready to discuss about the divergence as well as the curl. So let's start with divergence. Divergence is denoted as nabla.f, in which this will be something related to the dot product, but we'll ignore that first for now. So nabla.f would just be 1 over v, the limit as the volume goes to 0, for the surface integral f vector dot n hat in the d with the area. And this is integrated by the surface of the volume of the object. So if you're doing, let's say, this type of probe and you shrink the size, the surface will still be this one, while it will get much more smaller. So let's try to determine what will be the formula of the divergence when it comes to rectangular coordinate system. And the way that you could do this is by literally taking a cube, and then you would shrink the size until the size of dx dy dz. So you could compute the integral now. So you would have your your vectors as well as the n hats for each of the directions. So we could collect them into 1 over the volume, delta x, delta y, delta z, and there will be integrals, right? So for convenience, we'll just talk about the top side and the bottom. Sorry, let's just do the left-hand side as well as the right-hand side, which is separated by dx. First of all, the surface integral of f vector n hat dA would pretty much only correspond to a constant x. So, and also it will be in the direction of the x direction. So you would know that this integral technically is just, sorry, there shouldn't be any circle. So it's just fx of the particular place that we are interested in, x0, y, z. And so this is for this one. So this would be x0 plus delta x. So it would be fx of x0 plus dx yz. Now, a way for you to denote this in terms of differentials is that you could just denote this as x0 yz as well as the derivative partial fx over partial x times dx. So now, this and this would be subtracted, and thus the total for the opposite sides would just become partial fx over partial x dx. And why do we subtract it? It is because of the two different directions. Therefore, this side has positive, this side has negative, based on the coordinate system that you will use. So this is only for the x direction, but this would also work for any other direction. So there should be a dy dz as well, because there should be areas. So if you collect them all, you would get the partial fx over partial x, the partial fy over partial y, the partial fz over partial z, and there will be another delta x, delta y, delta z, in which it will cancel, and thus forming this formula for a rectangular coordinate system of the divergence. Partial fz over partial z. What if we are trying to solve this for a spherical coordinate system? So we could use the same idea by assuming a cube, like so. Well, it is a little bit slanted technically. And so we would have the dr in this direction, d phi in this direction, and sorry, this d theta, and this is d phi in that direction. So the volume of this cube should be dr, multiply this by r d theta, which corresponds to the length here over the change of the angle theta, right? So there would be r there. And then for in the d phi direction, it would be r sine theta d phi. So this will be our volume, r squared sine theta dr d theta d phi. And now let's just compute the surface integral. So now we could do the flux integral. So it's f dot the n hat of the delta a's, and this would be, first of all, in the r direction. It will be having the volume of r times r sine theta, or r squared sine theta, in the d theta and d phi, right? It has dependence on that. And then after that, there is also in the theta direction, which will be just the r sine theta as well as the dr. So it's r sine theta of dr d phi. Sorry for the flipping of the notation of the phi's. So this time the phi will be the circular one for the angle. Lastly, for the fy, this would be, for the fy, it would be in this direction, which means that it will have the dr and the r d theta. So therefore, we just need to write r dr d theta. And so this is only for the delta A. So if you sum them all up, and using the same logic as before, if there is changes in the value, you could just add you could add the partial derivative and multiply that by another dr or any type of value. So you could get the gradient, the divergence to be r squared sine theta of the dr d theta d phi, which will later cross out, and it will have partial over partial r of fr r squared sine theta, and then there's in the theta direction of f theta r sine theta, and lastly there's the 1 over partial phi, which is r f phi. And so if you simplify everything just by taking out all of the terms that doesn't have their corresponding variables, you could rewrite this as 1 over r squared of partial fr times r squared over partial r plus, let's don't cage that up then, plus the r could get out, that means it's 1 over r sine theta of partial f theta sine theta over partial theta, and the backside it will only have the r going out, so it's r sine theta of partial f phi over partial phi. And this is the gradient for a spherical polar coordinate system. So what does the divergence actually mean? So if we observe from the definition that we imply, we observe that this is the limit as 1 over v goes to 0 of the flux integral f dot n hat. Now you would know that f dot n hat would be positive as long as the f vector points outward of such object in total. So if you sum them all up, it would be the amount of vector field leaking out of the object. And that is what we can observe from the simulation that we given earlier. So this is the same simulation, but instead we could observe the orange circle going bigger or smaller depending on the divergence. If it is larger, it means that it has a higher divergence, while being smaller means that it has a lower divergence. So there's a theorem that we can imply from the definition of the divergence. If you take the volume to the side, and then instead of taking the volume, you could just take it to be a small volume, this would be the same thing as the surface integral of the f vector dot n hat dA, right? And so because this is dv, we should just add an integral at the front, just to make it non-differential. And what we observe here is literally the divergence theorem or the Gauss theorem. So it pretty much denotes how do you transform from a surface integral into a volume integral just by taking the divergence of such vector fields. So let's talk about the curl. So what is a curl? So we'll just define the value of curl, which I'll denote as nabla cross f, and this is defined to be the limit as the volume goes to 0 of 1 over v of the surface integral n vector cross f dA. So this has a different connotation with the divergence. Instead of observing everything that is going orthogonal to the surface, going orthogonal to the surface, instead it is asking about the vector field that is parallel to the surface. And this pretty much tells you about the spin of the vector fields, or the rotation basically. So because this is a very complicated thing to compute, we'll just actually assume that if we have an arbitrary volume here in which it has two parallel planes, as well as a strip that is revolving around these two planes, we could define an a vector in this direction. So if we try to figure out what is the curl in such direction of this a direction here, this would be the limit as the area goes to 0, in which this is the area that we're interested in, of this height here, which we'll call as h. So it's 1 over h times a of the contour integral of A dot n hat cross F. Now we could actually re-express this further just by using the property of the triple scalar product, in which this will become F vector dot A cross n in the dA. So what's A cross n? So at the top surface, this would just become 0 because A and n are parallel to each other, or negative, or anti-parallel. But when it comes to the strip here, it is always perpendicular to each other. If you have the A vector here, the n will go outside, and therefore you would have your direction to be in this direction. So we could just denote that as a very small length in here, or the dl vector. So it's f vector dot dl vector times the height. That's pretty much the area of 1 over ha, the limit as a goes to 0, which means we figure out another definition of the curl. The limit as the area goes to 0 of 1 over a of the closed integral of the path, not a, but we'll call this as the new path c of the path c, sorry, that's h. And you could cross out the h to be f vector dot dl vector, or pretty much just a line integral. So let's try to determine the curl in the x direction for a rectangular coordinate system. So let's just use the area definition. So we could get 1 over a of the closed loop of the f vector dl vector, right? And now, because this is the curl in the x direction, or in this a hat direction, we could just denote our a hat to be the x direction. So this is x, y, z. So which would mean that we would be interested in everything that goes in this direction. And so that means that this plate here doesn't have anything to do with this curl. So we just need to compute the rest of these contours. And so, because we know about the a vector now points in this direction, and the normal goes in this direction, it would mean that the a cross n would be in this direction. So we'll just assume that the height here would be constant, right? So this would mean that we'll just be doing the contour integral of this guy here. So if we do the contour integral here, this would be dy and dz. No, sorry, dy and dz here. So we can compute the area to be 1 over dy dz. And after that, for the contour integral, you could just do it piecewise. So if we try to evaluate each of these vectors and just compare the direction straight away, you could just get the fz and the dz. But because they are differing with the y, you'd get the partial fz over the partial y. And also you could do the same thing for the y. This would be in z. But there is also something that is interesting about this. This thing must be a negative, because there is orientation for such line integral. So it points in that direction, and then if you compare it to the one that is higher in dz, this would mean that it would go much more negative. So it would mean that it's the negative of the original function plus the partial derivative, which is why we get the negative here. So anyways, after we have already gathered everything up, we could figure out that this is partial fz over partial y, negative partial fy over partial z. So this is the curl in the x direction. But if you try to extend the curl in all three directions, you could just write this as the determinant of ijk of partial x, partial y, partial z of fx, fy, fz. And this will straightaway give you the vector of the curl. So let's look back into the simulation and see this magenta arc, in which it is spinning depending on the curl. If it is spinning faster, it means that it has a higher curl, while if it doesn't spin, it means that it doesn't have any curl. So the last thing to talk about the curl is that it also has the property similar to the Gauss theorem. The curl is defined to be 1 over a of the natural log of FDL, right, in the a hat directions, right? Now, if you move the a to the side and then do some computations of this, you could just technically get this curl FdA vector is the same thing as the closed integral of the contour here. Sorry, of the line integral. So now what you would get is that you could relate a line integral into a surface integral just by doing such transformations. And it is sometimes pretty useful to know about this because this will be implemented for Maxwell's equation. We can finally talk about what is the vector differential operator. Vector differential operator. Or we normally denote this to be the inverse of the triangle, or we call them as nabla, or del. So del here is defined to be I hat partial over partial x, j hat partial over partial y, and in the k hat partial over partial z. So if you use them for operations for scalars and vectors, you could do it by dot product, cross product, or scalar product. You would get the gradient, divergence, and the curl, which is why we use this symbol to denote curl, divergence, and gradient. So there are some properties of the vector differential operator. First of all, if you take the integral of a gradient, the line integral of the gradient, you instead only get the endpoints, something like that. So this is a very useful property to know because this is pretty much the definition of a potential. Second of all, if you take the gradient of the, if you take the surface integral of the divergence, the other two properties relate to the Gauss theorem and the previous one, which we call as the Stokes theorem. So it's the closed integral of FdL is the same thing as the surface integral of the curl. And for the closed surface integral, f vector dA vector, is the same thing as the volume integral of the divergence of the vector field. And also, the vector differential operator is linear, meaning that you could get something as follows. The gradient of the phi and b psi would just be these two things. If you take this for the divergence, you could get this to be such. And if you take the curl, this would be as follows. So it's a very useful operator and also something that is very easily that is trivial for you to use. So we can talk more about vector calculus. So in vector calculus, we can talk about more about the differential operators. So instead of only doing one, we can do it 2 times. If you do 2 different vector differential operator, you have 5 different combinations. First, if you take the divergence of a gradient, it's the same thing as calling that as the Laplacian. And it doesn't have any unique properties. If you take the curl of a gradient, this would be 0. It is the same thing as if you observe something that is trying to point towards the most high slope wouldn't really change its direction frequently. This is why the value is 0. If you take the divergence of a curl, this would be 0. And the logic is that since the curl is always orthogonal to the divergence, it's definitely going to be 0. And the last two vector differential operator would be the curl of a curl, and it will later be related to the gradient of the divergence minus the Laplacian. And that's the properties of the vector differential operators. There are more vector differential operators that I will show here. So here are the identities of such differential operators. And these 6 vector differential identities are normally used when you're dealing with multiplications of vector fields and scalar fields. So these are some identities, right? But we can actually get something much more useful if we are thinking about some particular functions. So we can start to think about, let's say, nabla.r, where r is just x, y, z. So if you do the divergence of such value, this would be 3. And you could also get the curl, it would be 0. Also, if you take the g, which is dotted by the nabla, r equals, and what you want to find is the value of this guy, you could just observe this. The dot product means that it will be gi partial over partial x and so on. And if you do it for the r, it will later correspond to the I hat, j hat, k hat, in which if you multiply that with the gi's, you would get just the g vector itself. And lastly, you could just figure out the Laplacian just by doing the divergence of such value, and it will equal to 0 anyways. Another thing that is pretty important is if you have a function that only depends on r. So fr or phi r, you would get your vector differential operator to be the r hat over r d over dr. If there's a function in which it depends on a dot r or phi a dot r, you would get your nabla to be the a vector over the derivative of a dot r vector. And if you have, let's say, a function that is dependent on the r, on big R, in which big R is just pretty much r minus r prime, the nabla will be the same if we assume that r prime is constant. Otherwise, if it's the other way around, nabla is negative nabla prime. So instead of only talking about the vector differential operator, we can talk about the vector integral theorems. So there's a very unique type of vector that we could consider. Let's consider the vector field to be psi of the nabla phi minus phi of the nabla psi. So if you try to do the surface integral of such value, you could just use the Gauss theorem to get the triple integral, or the the volume integral of this value here. And if you do the divergence of this vector field, you could just use the computations from before, and you would get this. And so if you try to figure out what's the divergence of such vector field, you could use the properties from above to obtain that this would be a nabla psi, nabla phi, plus psi of the Laplacian squared of phi minus nabla phi nabla psi minus phi Laplacian squared of psi dv, triple integral that. So this would be the same thing as taking the triple integral of psi nabla squared phi minus phi nabla squared psi dv. And this is what we call as the Green's theorem. So it will later be useful to know about this Green's theorem because this is where the definition of of most physical quantities come from. The other properties of vector integrals are as follows. So these are the four vector integral theorems that you should keep in mind. And so that's all for this video about vector calculus for classical electromagnetism. So thank you very much for watching. Make sure to like and subscribe. And also please share this to your friends who really wants to understand physics in a much more deeper understanding. Thank you very much, and I will see you on the next video.